each and every one of you for being here with us today. Before we get started, I would like to introduce myself. My name is Ria Agarwal. I am a student coordinator at Data Science Club, Amity University, Noida. It's a great pleasure for me to introduce our speaker today, who is going to talk us about the most trending topic, explainable AI. Mr. Abhishek Madan, currently doing MTech, Masters in Technology in Computer Science and Artificial Intelligence from Indraprastha Institute of Information Technology, second year. And next year, he is going as a SD2 in one of the reputed company, Dell. Currently, he is working in the field of explainable AI, and previously, he worked on projects like such as context based image captioning, dialogue based emotion classification, and automatic slide generation, uh, and many more. I hope the event will help you in the field of AI in making the machine decision transparent, explainable AI towards ethical, responsible AI. Abhishek, sir, now you can continue.
Hi Ria. Hi guys. Thank you for the introduction, Ria.
Yes,
Okay.
sir.
So yes, guys, I'm going to talk about explainable AI today. So like my voice is clear, right? Is there any noise?
No, sir,
No.
it's clear.
Okay. Okay. Sure. Okay. Let me share my slide. Okay. Is it visible?
Yes, sir, it's visible.
Okay. Perfect. Okay, guys. So I hope like you guys have a little bit of idea about what is artificial intelligence and machine learning. So what machine learning is that the machine learn things from the data. Okay. So I'm going to tell you an example how you teach a kid, right? So there's a kid and you give him chapters to study. He learns the chapters and you take tests, give him marks accordingly, and then he focuses on the things where he lost the marks. Okay, that's what a machine does. You give machine a data, you tell it to find the patterns and learn. It learns, you test it on a test set, give it accuracy, and that's how it learns, right? So that's what machine learning that's what a small subset of machine learning is, right? So why do we need explainable AI? Let's talk about that. So that's machine learning, you know that. So suppose there are many applications and uses of machine learning, right? It is used in medical area where you give in the details about your, suppose you give in the x-rays or CT scans of your lungs and tells you whether you have COVID or not. Okay. And whether you give the details about if you have flu, you need to find that you have flu or not, so you give the symptoms input into the machine and it tells you if you have a flu or not. Suppose you go to a bank and you tell a machine your details that if, okay, so let me show you this. Okay, so you go to a bank and you want a loan, right? So the bank manager asks you certain things about yourself, and it he puts the details in the machine, and then machine tells you if the loan is accepted or declined. So what they ask is your gender, if you're married or not, are you dependent on someone, your education, if you're self-employed, etc. Like loan amount, what is your credit history, if you have any property or you have previous loans. That's what the machine asked. Okay. And then features were extracted from the input that you have given, because the algorithm is already trained on multiple instances. Now it is just testing on your particular instance, on your data. Okay. So the machine tells that no, you cannot get a loan. So your loan is declined. But you would want to know that why is your loan declined, right? Because it's just a machine. It's saying that it's declined. Even the manager would like to know that why is it declined, right? That's why we need to explain the prediction given by the machine. Okay. That's why we need explainable AI. So that people who don't understand the mechanism of the algorithm can get to know why we need it. And there are other places also where explainable AI is required. Recently, the in law also it is used, and obviously in medical fields when the suppose you have to find cancer, you give the details of the patient, and the machine predicts whether the patient has cancer or not. But it's a very sensitive matter to tackle. If someone has cancer, then you need to give certain supplies to him or her. Okay, and you cannot just give supplies if someone does not have cancer. So that's why you need to explain why you have the cancer. Okay, that's why we need explainable AI in many fields. It's a very new field, and as you can see. Okay, all right. So yeah, how can I find the errors? How can I trust this? You need to trust the algorithm, right? So that's why if I give you an explanation why the loan got rejected, then you need an explanation. The user needs an explanation. Okay, so what is this? So let's say today you have a training data, and your machine learned the process, learned the function to predict certain things. Suppose you have two images, cats and dogs, thousands of images of cats and dogs, and those are labeled. You know what images are cats and what images are dogs, and you have given this input to the machine. The machine predicted whether it's a cat or a dog if you give a new image. Okay, that is what we have today. But tomorrow you might need why the machine predicted that it's a cat. So machine will tell you, okay, it has a fur, it has whiskers, it has claws. That's why. So it gave the reason, right? That it gave you an explanation. That's why it is a cat. So you got to know. Well, obviously, this is a very simple case in which you don't really need an explanation why is it a cat, because you can see it. But in many cases, you won't be able to tell. A layman who is not a doctor cannot tell if a CT scan of a chest is COVID or not. Okay, but if the machine can explain you why the certain things led to COVID positive, then it's explainable. Okay. Okay, so I hope you're familiar with decision trees and basic machine learning algorithms. So in decision trees, suppose you give certain amount of data, it can it can get you to know that certain attributes of the data led to certain leaf. Okay, so that you can see in the tree that why you got a certain prediction, which means it is very much interpretable and explainable. But as you increase the complexity of your model, the explainability decreases, the interpretability decreases. Suppose you have a deep learning model of multiple layers, multiple hidden layers, and you got an output of you have a flu or not. Okay, but you would want to know why certain which symptoms led to that particular output. But a deep learning algorithm can't really tell you that because it's a very complex model to understand by human beings. Only a machine can back propagate and learn the weights, but you cannot do it yourself that fast. So that's why you need to explain the prediction of that particular deep learning model or machine learning model, which is a black box for you. Okay, you don't understand what's inside it. You need to know why you got the output. Okay, so as the learning performance increases, the explainability decreases. As you can see, the top one in the graph is of deep learning, because of deep learning models are very complex to understand, right? But as you can see, the SVMs are very highly interpretable as compared to other models. Sorry, the decision trees are highly interpretable as compared to other models, as I explained, because you can visualize through the tree that why you led to certain prediction. Okay, so as you increase the complexity of the model, the explainability decreases. That's the trade-off. And to overcome that trade-off, we need models that can explain the predictions. Okay, so there are two kind of models, you can say. One is model agnostic and another one is model specific. What is model agnostic? So suppose you have trained a SVM with a Gaussian kernel on your data set to predict certain things. Suppose you are doing just a binary classification and you have trained a SVM, and you say, okay, but my explainable model can't really explain the prediction of SVM. It can only explain the prediction of logistic regression model, or you can say a tree based model. That's when it is a model specific. Your explainable AI model can only tell about specific models, cannot explain predictions given by other models. Okay, then that's when it is model specific. Model agnostic is exactly opposite of model specific. A model agnostic explainable AI model can explain prediction given by any kind of classifier. Okay, it can give a explanation of a deep learning model, whether it is a image based data is being used, or a text based data is being used, or tabular data is being used. As we know that there are many kind of types of data sets that can be used by any model. It can explain SVM with linear kernel, RBF kernel, or logistic regression. Model agnostic models can explain any kind of prediction given by any uh, ML model, any black box model. That's what model agnostic is. What is the scope of these models? So suppose you went to the bank and you want to know that why your loan got rejected. That's when it is local explanation. Only you are just trying to get to know why your loan got rejected. You don't want to know that why thousands of people's loan got rejected, right? You only care about your own loan. That's when you need the local explanation. Why would you need a global explanation? When you are trying to trust a whole machine, the like not literally the machine, the algorithm learned by the machine, then you need the global explanation. So what global explanation does is it explains the complete model based on certain number of predictions made by that classifier, made by that algorithm. Okay. So today mostly we'll be talking about model agnostic explainable models, which can explain any kind of model, any kind of black box model. Okay. So let's start with line, local interpretable, model agnostic explanations. So as I said, model agnostic. Model agnostic means it can explain any kind of model's prediction. And explanations, what are explanations? It will explain why you got certain output. What is local? It will explain one particular instance prediction. And what is interpretable? That you can interpret it. A normal human being who don't understand a black box machine learning model can interpret it from that explanation. So that's the full form of line, local interpretable model agnostic explanations. This was literally the one of the few first papers in XAI field, in explainable AI fields, which got famous. It is written by Sameer Singh, Marco, and Corliss. The topic of the paper is why should I trust you? Why should I trust the model? Right? Because it's a black box. You cannot trust it. You need to get the explanation, explaining the predictions of any classifier. That's why it is model agnostic. Okay. So, does anyone have any questions till now? If not, I'll continue.
I guess we can continue. There are no questions in the chat.
Okay, sure. Yeah. So, let's see what is line. Okay. So suppose we have two features, just two features in the model that you need to give to a model, and it will tell you if you will be having a stroke or not. So the purple, dark purple, or you can say dark blue dots represent stroke, and the light blue dots represent no strokes. So if you're, let's say the rightmost below blue dot, is it visible? Like, is my cursor visible to you guys?
Um, I guess not. Yes, it is. Yes.
Okay, okay, sure. Okay, so this rightmost instance is says that the feature 2 values is quite high, but the feature 1 value is quite low. Okay, and the model, the complex model that you have used, suppose you have used your RBF kernel support vector machine, it has classified your instance to being a no stroke, right? So that's what it has classified. You have this data, and this is what was classified. And suppose this dot, which is just on the topmost, says the feature 2 value is quite high, even the feature 1 value is quite low, which shows that you will get a stroke soon. Okay, so let's explain one particular instance. This pink one we are trying to explain now. Okay, suppose this is the guy, this is guy ABC, and he tells the machine that this is my feature 2 value and this is my feature 1 value. So please tell me whether I'll be having a stroke or not, or I have a stroke or not. Okay, so the machine now needs to explain. The machine cannot explain because it's not interpretable. So we need a line. Let's say we need line to explain it. Okay, how line will do it? Let's say this pink dot the line has to explain. Okay, so what line does is it'll go, let's just zoom in into that particular instance. Okay, we can see when we zoom into a curve quite like large, then the decision boundary becomes quite linear, which means we can just explain it using a linear model. Okay, which says that okay, the feature 2 value should be just greater, just less than this decision boundary. Okay, then it will be classified as no stroke. That's what this explained. But how do you train this linear model? That's what we need to do. Okay, so we'll come back to this optimization problem in a bit. So how Lime works: you select your instance that you want to explain. Okay, this pink one, we are trying to explain why it is being classified as a stroke or a non-stroke. Here it is classified as a stroke, so we need to explain why is it classified as stroke. What it does is it creates new data points around its neighborhood, around its proximity. It creates new data points. So these orange dots are the new data points that has been created by Line. Okay, so what Lime does, so I told you it's a linear model. So we train a linear model, we need to train it. Obviously, how will it tell the explanation if you don't train it, right? So you train the linear model according to the orange dots. You can see the new instances, create new data points in the neighborhood of the input data point, and then weight the new samples according to the proximity. Okay, so those orange points which are very far from the pink dot carry a very less weight than those data points, orange data points, which are very close to the pink dot. Okay. Now we have a new data set with X. We just have an X with the new data set. Okay. And then we train a weighted interpretable model on the data set, and then we predict the labels. Okay. So what this new linear model does is this will predict the labels of the orange data points around this pink data point. It will give weights to each of this data point according to the proximity, and then tell you which feature has more importance to predict if you will have a stroke or not, and which feature will have less feature importance to predict if you will have a stroke or not. Okay, so this is the optimization problem, that this is the linear model, this is how you get the linear model. Okay, so how do you know that which linear model will work better for your data set? Okay, that's what you need to find in this optimization problem. What is optimization? You need to optimize if you want if you want to minimize something or maximize something. What is argmin? Argmin means you need to find a G. G is just a interpretable model that you want to get, and capital G is a list of a large list of linear models from which you need one linear model which will explain your prediction. Okay, so you select many G's and then check the loss function according to your the complex model that you have. F is just a complex model that you're trying to explain prediction. Okay, G is the linear model. Pi x is the proximity measure, that how far your new data points are, how close the new data points are. And the second term is just the complexity of the linear model. So how complex it is. If your explanation model is too complex, how will it explain? Right? Because we are just trying to explain a complex model. If your explanation model is also complex, then it won't be able to explain the predictions. Okay, so that's why we have just selected the linear model here, because as I said, when you zoom into a curve large enough, then you'll get a straight line. Okay, so you need argument G belongs to capital G, means you need to find a small g which minimizes this particular loss. But what is this loss? This loss means that the prediction made by the function f, which you're trying to explain, and the prediction made by this new linear model that you want should be minimum. For which G it will be minimum, that what we get from the argument. Okay, that is the whole xi x here is. Okay, so what is this loss function? This loss function says to check the prediction given by the complex model that you want to explain, subtract it from the linear model that you want that you are trying to get. Okay, and give weights to it, because not every new data point has more important, like not every data point that you have created has equal importance. And that's how we create the loss function for it. And below you can see the proximity function. The proximity function is just the rbf kernel, Gaussian kernel, if you have heard about it. It is just a Gaussian kernel, which is an exponential kernel used in svm also. Okay, which gives the weights to the data points. So this is the loss function that you need to minimize to get a linear model. Okay, So this is a example of line. Okay. Suppose you have trained a model. Suppose you have trained a gradient boost or logistic regression model on data, diabetes data. Okay. You have given input like insulin. What is the value of the insulin in your body? Glucose. What is the skin thickness? What is your age? If you have diabetes pedigree function, I don't know what that is, that like a medical term. If someone is pregnant or not, how much is the blood pressure, and how much is the body mass index, BMI. Okay, so we have already trained on these features, given a lot of instances. Now you have given a test set. So this is person XYZ, and the person has given these values to the model. Okay, the model says that yes, you do have diabetes. Okay, now the person XYZ would like to know, why do I have diabetes? So this, the middle diagram you can see is line. It tells you that the insulin value, glucose value, age, and these certain features were the one main things, were the main features that led to your diabetes. But your blood pressure, BMI, and diabetes pedigree function were quite well, which went into opposite direction and told that no, you don't have diabetes. But the more weightage was given to insulin, glucose, and skin thickness and age. Okay, those were the main features that explains why you have diabetes. So this is a very good explanation, as you can see. If you show this to a layman, he can see that okay, my insulin value was large enough to get me diabetes, and my glucose value is also large enough. Okay, but my blood pressure is quite fine because it goes into a other direction of not having diabetes. So this is just an explanation given by Lime on your tabular data. Okay, Lime can also explain text data or image data. Okay, which we won't go right now. So the next model is next explainable model is SHAP, a unified approach to interpreting model predictions. So between SHAP and Lime, many explainable AI models came. Okay, such as Deep Lift, Gradient. So there was this gradient, integrated gradients. Sorry. So these many 4 5 important explanation AI models came between Lime and SHAP, but sometimes they were contradicting each other. Suppose Lime was saying no, glucose value was the main reason why you got diabetes, but integrated gradient method will say that no, pregnancy was the main reason. Okay, so both of them are contradicting each other. How will you unify them? So that's when SHAP came. SHAP tried to unify all these models and gave a new model which generalizes all these 4 5 models that I have mentioned. Okay, so you can say it is a better than Lime, but it can explain similar to Lime with certain variations, which I won't go why uh, it gave variations. Okay. Okay, let's see. So the paper says a unified approach to interpreting model predictions. The model that they have used to explain the predictions here are SHAP. SHAP is also a model agnostic method. As I said, model agnostic means it can explain any model. But certain parts of SHAP are also like they can explain specific models, such as kernel SHAP, which can, or deep SHAP. Deep SHAP can explain deep learning models better than normal SHAP, and tree-based SHAP can explain random forest or gradient boosting, XGBoost, AdaBoost, these kind of models, which are tree-based, which are decision tree-based. Okay, so this is what SHAP does. Let's see what it is. Okay, so let's see an example when there are 4 people in a competition. Suppose you go into a Kegel competition and your team has 4 members. Okay, and you won a prize of $10,000, let's say. How will you distribute it? You cannot just divide by 4 and distribute 2.5k dollars to everyone, because not everyone did equal job. So you can say, okay, I'll see if the player number 3 is not there, how much will we win? Suppose if player number 3 is not there, you win instead of 20k or 10k, instead of 10k you won only 5,000. So you cannot just say, okay, player 3 is worth 5,000, because that's just wrong. Maybe like player Player 3 also requires knowledge from player 1, which is a suppose the data set was medical data set, and so there's one player who is from medical background, there's one player who is a data analyst, one is deep learning expert, and one more, whoever you can say, visualization guy. Okay, so without one, how will you work? Without a deep learning expert, you cannot really do a deep learning thing, because a medical guy or data analyst guy cannot do it maybe. Okay, or maybe visualization guy don't do deep learning much. So everyone is important. So that's why we like check subsets of the players. Let's say if player 1 combined with player 2, how much will be the price? Combined with player 3, how much will be the price? And that's how you find the value of each player. This thing is a part of cooperative game theory, in which there are more than or equals to two players and you all got a profit, but you don't know how to distribute it among yourself. Okay, and similarly what we are trying to explain, right, we are just trying to give importances to features when we are trying to explain a prediction, right? So we are giving importances to each of the feature, and here what we are doing is we are trying to give prizes according to the importance of each player. So that's why we can use this method of shapely values of cooperative game theory into the field of explainable AI. So that was a really good idea, and nowadays many game theory concepts are being used in not just in artificial intelligence, in computer science also, right? Okay, so we need to find the contribution of each feature. That's when the idea of shapely value comes in. Game theory shapely values comes in. Okay. So, okay, as we know that how many subset does a n player game can have, right? 2 to the power n, right? If you have n elements in a set, then 2 to the power n are the elements which you get in your uh, superset. Okay, okay. So, how do you find it? Let's say there's a player I, okay, and there's this function f, this complex function f, which whose prediction we are trying to explain. Okay, so we have n number of features, and we are trying to find the contribution given by just ith feature. That's what this LHS means. The left hand side means that what is the shapely value of feature I, which means how important is the feature I given the black box model that is complex, you don't understand it, and the input data point for which the prediction you want. Okay, for which the explanation of that prediction you want. Okay, that's the left hand side. And suppose the feature that we are using here is age. Okay, as we were like as I said earlier about that insulin, glucose, the same thing is here. Age, gender, suppose age is 56, gender is female, BMI is 30, and she has heart disease. This is the instance, that's prediction we want to explain. Okay, and we are just taking the age feature here, and we just want ki age, how much was the age's uh, importance in the prediction. Okay, okay, all right, you understood what is the left hand side of the formula is. Let's come to the right hand side. The rightmost term in this in the square brackets you can see is fx z dash. Fx z dash means okay, so let's say you were just combining age and BMI both in the fx. You take all the features, age, gender, BMI, heart disease, and then check what will be the output. Subtract it without using age. Okay, so you put the age of that particular female and then got certain output. Subtract it from the function's output when you don't put the age of that particular female. Just put age as 0 or just mask it. Okay, there are multiple methods to mask a particular column. You can put all zeros, you can take mean, etc. I won't go into that. Okay, so you subtract it and then give weights to each of the subsets that you have made. Some subsets will be age plus gender, age plus body mass index, age plus heart disease plus gender. So the 2 to the power n subsets will be there. You give weights to them according to the middle term. M is the number of features that you have. Okay, the epsilon mark is obviously the factorial that you have. So that's how you calculate the shapely value. But you can say, okay, the two finding 2 to the power n subsets for each of the feature and then calculating its importance is too much. It's very it takes a lot of computational power to calculate those things, and that's why yes, SHAP is a bit uh, SHAP has a bit more time complexity than line. Okay, there are other methods which have came after SHAP line, like C explain, which has better time complexities, and it gives faster explanations than these models. Okay, so as I said, there are 2 to the power n number of subsets of a set. Okay, but you cannot really find for each of the subset and give the shapely values. That's too many subsets, right? That's why we have kernel SHAP. We try to approximate the shapely values for each of the uh, feature. Okay, how do you do that? You train a basic linear regression model. Here x1, x2, x3 are the features. Beta 1, beta 2, beta 3 are the coefficients that will be trained, and these coefficients signify the importances given to each of the feature. Okay, that's what kernel SHAP is. It is faster than the vanilla SHAP, obviously, because it just approximates the uh, values given to each subsets, and that's why it's faster. Okay, let's see. Okay, so suppose you go to you have some symptoms. You go to doctor. Okay, you have a cold, just cold. You just told the doctor that you have cold. Okay, so doctor says, okay, maybe you have flu. He or she, the doctor, will do more tests on you, maybe. Okay, he'll tell you, okay, yes, you have a flu. So after each of the symptom you tell the doctor, he will conclude whether you have or you don't have a flu. Okay, so at start, obviously, the probability of you having a flu can never be absolutely zero, right? It will always be something. Suppose that something is 50. Okay, that is expected of fx, which means everyone who comes to the doctor or everyone in the data of the machine has certain probability of a flu. Okay, that's when 50 comes in. That nothing is absolutely zero. You have 50. Okay, then you give one more feature to that machine, that okay, my age is this. So this particular example, as you can see, 46 years of credit history. This particular example is of bank loan thing, in which obviously bank will not reject your loan just by looking at you, right? You will have certain probability of expected value of fx, for which it can say, okay, yeah, you can get loan. And then you tell the bank your age, which increases your probability of getting a loan by 5 1. And then you tell one more feature, 5 2, one more, 5 3. But then you tell bank something which decreases your chance a lot. Okay, you just told the bank that you are 80 years old. Okay, but how will you return the loan? But if you die in 1 year, right? Maybe. I mean, who lives more than 100 mostly? So yeah, so 5 4 maybe age was the major factor why it decreased your chance of getting a loan. But then you told the bank that you have 46 years of credit history, which is really good because you were paying your debt and everything on time always. So which increased your chance of getting the loan a lot by 5 5. And the final score you got was 22%. Okay, but 22% is not really a good percentage of you getting a loan, and that's why it got rejected. It should be more than 50% if we are just using a sigmoid model. If you know about it, it is used in logistic regression, right? So yeah, this is the explanation given by Shapley to a person who wanted a loan and gave its features. Okay, so yeah, that's why you need explainable AI. It's important for every most of the fields in which the machine learning models are used, and they are complex in nature. So this is also an example in which you want to know whether you have diabetes or not. Okay, so the pink part on the left hand side goes more into the part in which you have diabetes, and the right hand side part, BMI, age, pregnancy, go into the part in which you don't have diabetes. So the part which gets more of the probability will be the final prediction, right? That's how it works, right? It's the majority probability gets becomes the final prediction of the model. Okay, so yeah, this is also on the tabular data of diabetes on some particular instance. So all of these examples that I've showed you were the locally based because they were just trying to explain one particular instance. But when you're trying to explain more than one particular instance, not just more than one, all combined, you're explaining a model, explaining a black box model, that's when global explanations comes in. And we have a special case of global explanation for line known as SP line. I don't think we have time for that right now. Okay, I think that's it for now. If you have any doubts or questions, I can answer. Or if you don't have any doubts, then that's fine.
Thank you, sir. The event was very informative and was really enjoyed listening you.
Thank you.
And thank you everyone for being a patient listener. If you have any queries, you can ask or you can write them on the chat box too. I hope you all enjoy this amazing event and learn something from it. Any queries, anyone?
So the event was very informative. If anyone has any doubts, you can ask in the chat right now or in the WhatsApp group that we have. We can take them now or mm,
Okay, and if you guys want to discuss anything regarding my research or AI, free feel to mail me. Okay, I've
yes,
written
sir.
my. I'm just typing my email ID right now.
Thank you, sir. Thank you for your time.
Okay,
Thank you, sir. The event
Thank
was really informative and
thank you, sir.
structured. Different.
thank you.
Thank you so much, sir.